Oh, how about now? It was muted. Oh, yeah. It's right. We're agile. We're iteratively improving. So, are we good? All right. So, welcome everybody to Right Brain Networks. We're going to be talking tonight on beating the odds. A little bit of a misnomer. We're not actually doing statistics, but playing some math games with Lambda. It was one of my goals to become proficient with Lambda and API Gateway. And the way I usually do that is just by taking some problems that I'm familiar with and trying to solve them in a new way, getting familiar with the utilities, and that's kind of what I did to start here. We've done a lot of Lambda talk, so I wasn't planning on going too deep into Lambda, but we have a lot of new faces today. So if you'd like me to, just let me know. I'm happy to dive as deep as you'd like. Although if we get too deep, we can do it afterwards. Just chatting. So yes, it is time to get super mathy. We're gonna solve three separate problems tonight using Lambda, parallelizing the problem across multiple functions. We're gonna do a Monty Carlo simulation of doing an integration. Has anybody here not taken a calculus class? That's fine. Doesn't matter. Doesn't matter. Not a problem. Don't worry about stats. Stats was I was a math major. Stats was my least favorite math class. I'm going to avoid it if I can. We're going to do an approximation of the number pi. I'm sure everybody's heard of the number pi using a Monty Carlo, and I'll talk about what that means in a sec. And the last thing is we're going to take a look at visualizing the Mandelbrot set using Lambda. These are the kind of the three problems that decided to play with. Monte Carlo simulation is really easy. All it means is trying something over and over, usually thousands of times, and using the results there to figure out the answer to a problem. So let's say you wanted to figure out what are the odds of getting heads flipping a coin. Flip a coin 10,000 times. See how many times you get heads, how many times you get tails. That's a Monte Carlo simulation. It's really useful for gambling type, playing games in general, which is why they call it Monte Carlo. And it's important that something be random, otherwise it's not particularly interesting. Yes. Okay. So who am I? My name is David Barnett. I work here at Right Brain as a software engineer. When I was in college, we always made fun of the computer science majors, called them defrock mathematicians. So now that is me. I'm a defrock mathematician. I spend most of my time developing in Python. I really enjoy teaching, so if I get too teachy and lectury, just raise your hand and say you're being too lectury. I'm happy to cool off, and some of my other creds there as well. Why? Why would we want to do this? Why use Lambda to solve these math problems? Is Lambda faster? Definitely not. Lambda's great for parallelizing. You want to be able to respond to 1 or 100,000 requests. Lambda's really good at that. But it does take a microsecond for to spin up. It's some sort of container service on the back end, so it takes some time to get your code there. It takes some time to get your code running. It's not a huge amount of time, but there are faster solutions. Is it easier? Definitely not. Come on in. Lambda is pretty easy, but for these kinds of problems, there are better tools. But is it a choice a reasonable human would make if they were actually trying to solve these problems? No. But it's a great thing to do just for fun. My whole life, I've always wanted a theorem named after me, so I decided to name my own. So now we're going to learn Barnett's theorem, is you never really know your tool until you've learned how to abuse it. That was why I wanted to do this. Lambda being my tool. What is Lambda? Talked about it a little. Lambda, it's a function runner within the AWS ecosystem. You define a function, you define how it's going to get called, you define the data that's going to come in, and then there's some sort of event-driven trigger that will launch your Lambda function, and you can get your output back out. All right, don't worry about it. No math on the test. If the math doesn't make sense to you, I'm going to try and abstract all that away, and we'll just have some fun. All right, so the first thing we're going to do is approximate the value of an integral. What's an integral? Super mathy, but you don't need to know that much. All you need to know is an integral is the area under a curve. And what we're particularly interested in is what's called a definite integral, the area under the curve within some bounds on the left and on the right. So just think of it as an area. We want to approximate this area. The way we're going to do that is by picking points somewhere within a box around this curve. We're going to pick a point and we're going to say, is the point underneath the curve or is the point above the curve? Once we've done that, we can use the percentage of the points that are below and above to approximate the area. At this point, it would be reasonable to ask, is this a good way to solve this problem? Anybody? Nobody's going to ask, is this a good way to solve this problem? Of course not. This is a terrible way to solve the problem. We have way better ways of solving these kinds of problems, but it is fun. It's something to do to get more familiar with Lambda. All right, so let's do it. We're going to start with a really simple function, x squared, basically y equals x squared. And we're going to approximate the area under the curve between -1 and 1. I picked a really easy function because the hardest problem of doing one of these simulations is knowing the bounds. You want to make sure your whole function is inside your box. So I picked something really easy. You could do this with any function. Doesn't really matter. If you had a particularly nasty curve, this might actually be a reasonable way to figure out the area, although there are better ways of approximating it. The method we talked about a little bit. We pick our box. We pick a random point in there. We see whether the point is under or over. And then we count the number of random points that are under. And then since we have a box, the number of points under divided by the total number of points gives us the percentage under, times the area gives us the area under. Let's try this demo, a single Lambda instance calculating 100,000 points. It's really impressive to me how quickly this works. So, that's slack, we don't want that. We'll get there later. So here, we have the Montegrate function, using Monty Carlo to integrate. I can get into the Python, not planning on it, but basically what we're doing here is iteratively taking 1,000 points and just keeping a count of how many of them are above and how many of them are below and the total amount. When you have your function, how many people are familiar with Lambda? A little bit, some people not. So for this one at least, I'll show you, we defined the Lambda function and the entrance point. So this is the function that will get called, Montegrate handler. The default Lambda function is Lambda handler, so that's kind of from a naming convention. That's the only reason it's called that. And you'll see here, we have this function, creates an instance of the class up here, says count the number below, and then return a JSON structure with the results in there. We can, the interface for Lambda is actually pretty nice. We can just run it by clicking test. See, turns gray here. And within a few seconds, we get a result back. We tested 100,000 random points. We found 33,298 were below. And the approximation we got was 0.665. Turns out the actual value is 2/3, 0.666666. Not a bad approximation there. So,
and what did you write the code in?
The code is in Python. And if people are interested, I can upload it to GitHub. Not a whole lot of magic in the code, but happy to share it. So that's great. One of them is probably good enough. In general, 0.66 is going to be good enough for whatever we're doing. But what if we wanted to do 1 million or 5 million or 10 million iterations? What could we do there? Well, since Lambda is kind of infinitely parallelizable, we can just spin up 100 of these Lambda functions. So let's do exactly that. Just so happens I have a Python script here that does exactly that. You'll see here we're going to run 100 invocations of Lambda, parallelized across, don't worry about too much about the Python. I'm parallelizing across 20 processes So I'll be launching at most 20 at a time. And each one of those will gather the JSON results. We'll add up the total number we found below, the total number of points we did, and we'll get an approximation. Again, if you want me to go into the Python, I'm happy to do that, but it might make more sense to do that after. So we'll call it. And I tried doing, we're doing 10 million now. I tried doing 10 million on my laptop. It took about 200, I think it was actually about 25, 30 minutes to actually run. Doing it here takes, I think, about 13 seconds. So we were able to parallelize across all of these. We've got our result, and you see we've got even more fine-grained approximation. 0.666 before we had 0.66. This was with 10 million points. 100,000 per 100 invocations. This is the x squared. Yep, and from -1 to 1. And so here we've got a slightly better approximation running 100 million or 10 million points. Again, not a great way to do this. If you needed an approximation of this integral, there are better ways to do it, but this is a great way to use Lambda, which was the goal. All right, so what next? Let's approximate pi. Yes, absolutely. Wait. This is our microphone. Can somebody toss this back? That's right, yeah. Yeah. So there is a spin-up time. It's generally sub-second. It's always sub-second. It takes about, in my experience, between 1 and 200 milliseconds to actually spin up. It's very quick. Now, I've built a system where I've sent a request, and I'm expecting a response, and it is noticeable. So if you need that 0 response time or near 0 response time, Lambda is not the utility for you. If a couple hundred milliseconds is fine, Lambda is great for that. Okay, that's fair, right? If you need a JVM, it's going to take longer. Lambda will run with Java, with Python, with Node, and does it run with Ruby yet? Not yet. Okay. All right. So thank you. That's a great question. One thing to note, there is another utility which we'll get to. I'll save talking about it, but that's API Gateway, which gives you a web endpoint to trigger and pass data to Lambda. Not using it for these first two tests. So use case number 2, approximating pi. This problem is very, very similar. I love this. I remember doing this in, I think, 6th grade, sitting in class. My teacher took a box, drew a circle in there. Everybody got a penny. We flipped our penny into the box. We counted the number that fell inside the circle, the number that fell outside the circle, and we used it to approximate pi. We're going to do exactly that with Lambda. Where's my mouse? There we go. All right. So we're going to take a circle. We know that the area of a circle is the radius squared times pi. We're going to take our square. We know the area of a square is the length of one side times itself. From that, we're going to take some number of points. We're going to figure out the number that fall inside. Figuring out what falls inside is very easy with a circle. If the distance from the circle, or the distance from the middle is less than your radius, it's inside. It's the great thing about circle, same distance in every direction. So what we know is if the area of the square is 4 times the radius squared, because the radius, the length of the square is 2 times the radius, times 2 times the radius gives 4 times the radius square. The area of the circle is pi r squared, as we hopefully remember from geometry class. We take the ratio of points in the circle to points in the square, divide out, we get pi over 4. So if we take that ratio times by 4, we should get pi. It's very, very similar to the integral, but now we can get an approximation of pi. Is this a good way of approximating pi, you might ask? Nobody's good. Thank you. Thank you for asking. No, of course it's not. We have way better ways. We know pi to a trillion digits. Pi past 4 or 5 digits is totally useless. It may be 20 or 30 if you're building a GPS system. Beyond that, totally useless. But some reason we love to calculate digits of pi. But who cares if it's not a good idea? It's still fun. let's see what happens with 1,000 points. If we do 1,000 points inside or outside of the circle, what kind of an approximation do we get? We'll go back to Lambda, to our second function, which this is my favorite. I got to call it Monty Pie because it's Monty Carlo and Python. Yeah. It's only a flush one. So it's very similar function. We're counting number inside, number outside. We're running 1,000 times, and we're going to give an approximation as the formula we showed before, multiplying by 4, dividing the inside by the total, and it should just take a few seconds here. And we get a pretty darn good approximation of pi with just 1,000 points. Yep. And so we got a delta, the first, looks like, I can't really see, the first three digits are totally correct. And we're not that far off past that. So 1,000 points is enough. But the whole point of this is not to do good math, or not to get a good approximation. It's to have some fun. Let's see what happens with 10,000, 50,000. Let's go all the way up to 100,000 points. See what happens. Again, we're going to go back here. I have another function here. Looks very, very similar because it's mostly cut and paste. What we're going to do is we're going to run 100 invocations of this Monty Pie function. Take all the values, add them all up, and then see what we get. Let's run it. For some reason, this one takes a little bit longer. I haven't been able to figure out why, but it does. I think it takes about 20 seconds. Not too bad. But
just the function, it's just the structure, what you're counting. It's the same, you're 1,000,000 points, you're in the same comparisons. It's just a different thing that you're comparing.
The only thing I can think of is I'm doing a square root here, right? You use square root to figure out how far you are from the center. It's a slower function than we were looking at before. I'd like to run an analysis on it and see where it's spending most of its time, but that's my guess. There we go. Now we've got pi. Actually, we got a worse approximation this time. That hasn't happened to me before. But we're picking random numbers, so you never know what's going to happen. Usually here, I got to four correct digits. So we were able to parallelize. We were able to do here 100,000 points within. Did I run time on this? I didn't. I think it's usually between 13 and 20 seconds. So pretty darn quickly. If you did have a numerical problem, would this be a reasonable tool to use? Absolutely. There are better tools we have for approximating pi, better tools we have for integrals. But if you're doing some kind of numerical analysis that nobody's ever done before, and you just needed a lot of compute, this would be a great way to do it. So the pattern here makes sense, even if our specific examples are just fun, just for fun.
If your function's easier to describe in a rules-based system than a math equation, then it might be easier this way.
That's true. Yeah. Yeah. If it was non-continuous, if you weren't able to use your normal tools, yeah.
Or you want to do just a Sierpinski gasket and see what it is without if you're,
Yeah, that'd be a lot more reasonable. But that would know how to write a code.
Well, right. Yeah.
So, use 3. We're going to get a little bit more mathy here, but we're going to get a really pretty picture at the end. So, if nothing else, we'll get a really pretty picture at the end. We're going to visualize Mandelbrot. Does anybody here know what the Mandelbrot set is? I know you do. No, great. Even better. Okay. So what we're interested in is just our normal plane from -2.5 to 1, -1 to 1. Just a subsection there. We're going to get really mathy for 1 second. Feel free to tune me out. Really what we're looking at is the complex plane. Here's an example of what I mean translating from a point to a complex number. If it doesn't make any sense to you, doesn't matter. I just wanted to point it out. All right, so what is the Mandelbrot set? Well, let's say we take any point in our boundary and we square it. And then we add the original point to it. And then we do that over and over again. And we do that, let's say, 50 times. Some numbers stay small. Some numbers get really large. The Mandelbrot set, all it is the numbers that stay small. We can say that if we run 50 times, we can prove that that's enough. And if we ever grow larger than 2, we can prove that we will also go off to infinity eventually. We're not going to prove those tonight. I don't know how to. Anyway, This makes it. This is just computationally what we had to do to figure out each point. Now we're going to do several, I think a couple million points. So that's pretty expensive. It can take a long time, especially with Python and the imaging libraries that I've used. So is this this is, again, probably not the right way to do it, but it is cool. Why is this set cool? This is the image we're going to create. This is the Mandelbrot set. This is the kind of thing that makes mathematicians weep. We love this kind of beauty. All of black are the Mandelbrot points. Any point that is black is in the Mandelbrot set. Not too interesting in the middle, but along the edges you get these incredibly complicated curves. So complicated that if you zoom in on them, it doesn't matter how far you zoom in, 100 times, 1,000,000 times, 1,000,000,000 times, 1,000,000,000,000 times, it doesn't matter. You can find the original shape somewhere within that boundary. It's complicated all the way down forever. This is why I love this problem. So what's our plan? This right here was the first thing I wanted to do to Lambda, and it kind of spawned the idea for this talk. This image, if you think about it, is just like a map. And if you want to explore a map, you use Google Maps. Google Maps is great. It's got an API for building your own maps. I tried using Google Maps. It worked mostly. It's got some logic there for dealing with as you go towards the poles. You've got a smaller diameter of the Earth, and it warps things. And so there's ways around that. I couldn't figure it out. So thanks to Dario, who's working back there, and his JavaScript magic, we found another utility for doing mapping, very similar to Google Maps. As a matter of fact, you can actually do street mapping with it, but we use that instead of Google Maps. But you could absolutely do this with Google Maps. The way Google Maps works is you don't get an image. You get a bunch of small images, and it sticks them together, and as you drag, it moves them all, and it takes care of all that for you. The thing that Dario found and helped code up was exactly the same kind of thing. The problem then becomes, how do you build these tiles? Well, you can pre-build all the tiles. You can, but then if you want to go in arbitrarily far, you don't have pre-built tiles. You can try to build the entire thing as an image. It's possible, but it takes a very long time. And you could have one function out there that builds a tile, and then builds the next, and then builds the next. But this seems like a perfect job for Lambda. We want to build 100 tiles, call 100 Lambda functions. We want to drag really fast, keep calling more Lambda functions to build more tiles. Is this a good idea? One might ask. One might not ask.
Is this a good idea almost?
Actually, this one isn't a terrible idea. There are faster solutions. If you ran Apache, if you ran Nginx, and you had something persistent there, and you wrote it in C, and you used a faster graphics library, you could do it faster. But actually, using Python and Lambda here works pretty well. So the operations here are far more interesting than the last two problems. So let's actually take a look at it. This is how I built this system, how Dario and I built the system. The user makes a request through the map API. The API hits Amazon API Gateway. Let's talk about that for a second. API Gateway is a relatively new utility from Amazon by which you can define an endpoint. And you get an endpoint from Amazon, HTTP, some long random string, Amazon, AWS.com/whatever. You can define what data you're going to get, what data you're going to post, what data you're going to pass along in the post, and it translates it potentially to JSON, which is what we do, and then passes it on to Lambda. Very, very cool utility, very, very hard to work with. Amazon knows this. They're working on it. They're trying to make it easier to work with. But right now, the interface is very confusing, especially if you're passing data around. But thanks to Tanya, we got it working. Thank you very much. The Amazon API Gateway expert. And so what we do is we pass in which tile are we looking for and what zoom level are we at. It's all we have to pass along. Then there's a Lambda function, just some Python code that generates a particular tile based on which tile we're looking for and how far we're zoomed in.
So the user request is to say, I want to look at this area at this zoom. Is that what the user request is that you're saying is passed to Amazon Gateway?
really, technically, the user request is to the map API, and then the map breaks it into tiles and says, I want this tile, and this tile, and this tile, and this tile. But it doesn't make one request. It makes one request per tile, which is where Lambda comes in. Why Lambda is really actually kind of good for this. And so the user request, I want to view zoom level 4. And then the map says, I want tile 1, comma 1, zoom level 2, 1, comma 2, zoom level, and so on. Lambda looks in S3 and says, have I built this before? If it has, it just redirects the user, the particular request to S3. So we don't have to rebuild the tile every time. If it's not, it builds it, puts it in S3, and then redirects the mapping interface to S3. So we're actually serving the data directly from S3. S3 is really good at this. You can use it as a web endpoint. So again, the request comes in from the user. We get which tile we want. We respond with, here's the location of the tile, and the mapping interface goes ahead and displays it. Using Lambda with a library like the Python imaging library, which is what I used, is a little bit difficult because there's C code there. So if you are going to build a Lambda function and use a Python library that has C code, you need to statically compile that library because you can't expect that any of your dynamically linked C libraries are going to be where you expect them to be. Lambda is a very specific environment. It's very, very locked down because they don't want you to be able to use it as an entry point, reasonably from a security standpoint, but it does make working with libraries which have statically compiled code a little bit difficult. Anyway, it's not impossible. It wasn't too hard with the imaging library. It's very hard with some of the database libraries, but there's some really nice blogs out there that talk about it. So let's take a look, see what happens.
So that sounds like that was some problems.
You involved a number of different individuals to assist you with this. There were some.
Yeah, we spent some
steps.
time on this one. Yeah, but I think we all learned a lot.
Yeah.
One of our core values is be curious. So I feel very comfortable asking people to kind of help me solve those kind of problems, which is fun. All right, so we're going to go back to our web browser. This is what we are eventually going to render. This is what it looks like when it is completely rendered. Now let's see what happens when we do a fresh call. And I have another window just in case this doesn't work well. You'll notice the tiles. This is what Google Maps and all of these mapping interfaces are actually doing behind the scene. And you'll notice it loads one tile at a time, one per request. We can actually look and see the request going out. We can zoom all the way out and see it happening again. This is where, for some reason, sometimes it doesn't render. We'll give it a few seconds. But what you're able to do is zoom in, get a new set of tiles, zoom out, hopefully get a new set of tiles. Yep, there we go. And you can explore as deeply as you want. Centering is difficult. Sometimes you just end up with a whole bunch of blue tiles, and trying to figure out where you are can be a little bit difficult. And that's actually the biggest problem I had with this was figuring out the zoom ratios. It's not like you zoom in one and you're twice as big because you're talking about something designed to do, okay, you're at a country level, you're at a city level, you're at a state level, you're at a county level, and so you have to do some fudging around their particular ratios to figure out what points you want to be at. And now that I've zoomed in pretty far, I'm working with some very, very small numbers, which is computationally very expensive, and it can take a while for these tiles. I'm going to zoom out here.
Very small numbers that you have to iterate no more than 50 times.
That helps a lot. That does help a lot, but still, so yeah, this is the problem.
Did you put a limit of 50 in there just to make
I
sure?
did put a limit of 50.
Okay,
Yeah,
great.
and if you notice, when we were zoomed out, it was not consistent blue. It was different levels of blue. That the deepness of the blue has to do with how quickly it went off to infinity.
Well,
That's the
right,
contour.
yeah.
It
so
still goes off to infinity. It just goes off slower. Of course, it's not. Yeah, it would be, now that I've got this all set up, actually just doing the computations would be relatively
They're
easy, I
beautiful
think.
too.
Oh yeah, there's no lack of these
Yeah.
beautiful complex fractal sets.
Oh, there's a language too.
Yes.
Yeah, but I know somebody that's the love of his life. He said.
Did Julie say?
No, Julia,
the
the
language.
language. Yeah.
I know some people who really love it, and it is specifically designed to do parallel computations. Maybe I could try to do the Julia.
Wow.
Julia.
Ah, that's awesome.
Get totally meta.
Yeah.
And there you go. So we've zoomed in, and we're able to take a look at a slightly more detailed view.
I've noticed that when you drag, your squares pop up faster than when you zoom.
I don't know why.
Okay.
And I've watched the Firebug or developer tools, and I see the request going out and coming back very quickly. I don't know if I don't think it's Lambda spinning up, because Lambda's not that slow.
Mhm.
It may be something in the mapping utility I haven't been able to figure out. But yeah, I've noticed that as well.
Maybe the mapping utility is caching nearby squares.
I don't know, maybe. Dario, do you have any idea if it does that?
No, not really. It happened both with Google Maps and.
Yeah.
So what is this mapping utility?
This was from D3, I believe.
Yeah, it's V3 with custom geo tile.
So if you did have data to represent, this would actually be a pretty good pattern of how to do it, assuming that you could partition the data into 250 by 6 by 256 square blocks. You can actually modify that. We had some trouble with it doing 100 by 100, which would have been really nice because it renders very quickly. But yeah. So this was the third utility I had planned to look at. We're about 30 minutes in.
How when you say computationally
Expensive. What? I don't have a scale, an idea for what that means.
And that's fair. Any one of these points is not particularly computationally expensive. All we're doing is squaring a complex number, adding another one to it, squaring it again, adding another one. It's pretty inexpensive. But if you think about how many points we're testing here, that's really where it becomes computationally expensive, because each of these tiles is 256 times 256, then probably times 50 times 50. That's a large number of points to be calculating. And that's where the computational expensive or cost comes in.
And if eventually it's billed, is it?
Well, less than a penny per
That's a great
rendering? Or?
So it's way less than a penny per
Right.
rendering.
Okay.
If you look at S3, each of these tiles is somewhere between 256 bytes, which I think is just the pure blue. And I think the largest I saw was 1.1K. Storing data in S3 of that scale is very, very inexpensive, right? I mean, storing a gigabit per month is like 10 cents. So we're talking about maybe 5 cents per month to store this whole
And
thing.
what about the computation, the use of the lambda?
So an invocation of a Lambda function, the first million are free. The next million cost a penny. And so but you also pay for compute and memory. Each one of these tiles I'm able to compute within 3 seconds at 128 megs of memory. And I think that a single invocation is like 0.00000. It's like 9 or 10 zeros, 3. It's very, very inexpensive to use Lambda. I'm as somebody who goes out to customers and talks to them about using Amazon as a tool, I push Lambda really hard. It's a great way to save money. If you've got something that's going to be called a few hundred, a few thousand, maybe even a million times a day, use Lambda if you can. It's great. It's cheap. You don't have to worry about EC2 going down. You don't have to worry about your instances being what's the word, like well, yeah, that's interesting. I hadn't even thought about the DDoS, but like you get notices from Amazon saying we're going to decommission your hardware. You need to spin up on some new hardware. You never have to worry about that with Lambda. You never have to worry about security patches. You do have to worry about the limitations in terms of time. One of the first times I tried to do Lambda was I tried to parse some very large XML files and put some data into a database. Seems like a very easy task. But we were talking about XML files that were on the order of half a gig. And I couldn't do it within at the time it was a 1 minute window. Couldn't do it within there. There was no way around that. Now you have a 3 to 5 minute window, 5 minute window. Could probably do that, but still Lambda's not really great at that.
What happens after 5 minutes?
It just dies. It just turns off.
Instance
there is no way to handle errors, which is one of the drawbacks.
I was going to ask you a question.
Okay, but within Lambda, you can say how much time do I have left. So you can code your way around it. If 99% of what you have to do, you can do within 5 minutes, and the other 1% you don't care that much about, you can check every once in a while and say, am I close to 5 minutes? And shut yourself down and just maybe move that into another bucket that's unprocessed, something like that. You cannot save your state. You could push your state to Dynamo or to our like a relational database or something, but you can know how much you can get a context. There's a context object. Actually, let's look at that.
Serializable object.
There's an object that gets every Lambda function. Here's the ingress gets two things passed to it. One is event. An event is a dictionary in Python. Is a dictionary with the data that you've passed in. So, for instance, in this case, I would. Okay. Well, okay. In the case of the Mandelbrot, I'm passing in the x coordinate, the y coordinate, and the zoom ratio, the coordinate of the tile, not the point. And then that gets passed into that event as a dictionary. The context is something Amazon specific. You can get all kinds of information like, where am I? Am I in US East? Am I, how much time do I have left to run? There's a huge object there with a bunch of information that you can grab out of Lambda.
Have you ever tried to call yourself from within Lambda? Say you're running low on time and just pass yourself your stuff again?
You can, for instance, those invoke functions where we ran 100 instances, that's just Bodo. And Bodo 3 is available, at least within Python. So you could use Lambda. Right. One of the things about Lambda is you can't connect to Lambda. Right. You can connect to an EC2 instance. You can look at syslog. You can see whether you ran out of memory. Lambda logs to CloudWatch, and you can get a lot of information, but you'll always be able to get more information by SSHing into an EC2 instance and doing diagnostics that way. So if you are trying to keep state over a long period of time, you're going to have to be really careful if you want to do that. Now, if they ever support Lisp or something like that, and you wanted to, and you wanted to just call off functions as actual Lambda functions, that would be extraordinarily cool. I don't know how efficient it would be. I don't know how quick it would be able to run. One thing interesting about Lambda, if you run a Lambda function, let's say it takes you 200 milliseconds to run. And you run it again, you can expect to see it's going to run about half a millisecond. Because the first time it runs, it's building some sort of container. And the second time, as long as you've done it within a short period of time, it's still there. And so that's something to keep in mind. If you're going to be running something once every great amount of time, you do have to eat that cost, that initial startup cost. So that's really all I have as far as slides. We've had some questions, but if there are more questions, if you want me to dive into some more of the infrastructure or the code, happy to do that.
Can you talk a little bit more about the context? So if you have, I don't know, connections that you need to make to a Dynamo or S3 or whatever, is that what comes through the context?
No, the context is information you can gather from Amazon about the context of your environment. I haven't. The only thing I've used it for is figuring out how much longer I have to run. There's a lot of other information that you can get out of it.
So if you want to do some kind of configuration where you need to access resources, how do you specify
That's
that?
a great question. So let's look a little bit at the Lambda configuration. So when you are creating a Lambda function, you can put your code in directly. This is not the normal way to do it. I did this so that we could actually look at the code. Normally what you do is you build a package, a zip package. You can either put it in S3 or you can upload it from your laptop. That zip package is going to contain your code, and you define the entry point. I'll look at that in a second. And it's also going to contain any libraries that you need. So for instance, I use the Python imaging library. I put that in my zip file, and it was just there. You have it in the root, and that is where, at least for Python, that is where Lambda will look for it. That is, it has the root of your zip package as part of the path that it will import from. As far as configuring to connect to other resources, each Lambda function is given a role. This is an AMI role. You can define a role. For instance, when I connect, one of these, I actually upload all the data. My original thought for the Pi was to put all of the data into Dynamo, given a single runtime, and then I would do a query and get all of the data on the runtime, and then sum it up. And then I realized, I'm calling this from Python. I can just get the data directly. I don't need that. But the way I connect to Dynamo, what I had to do was create a role with Dynamo put data access. Let's see if I can see that from here. There's not going to be anything secret if I look in the IAM. I'm not, well, even then I can only expose the public. I can't even get to the private anymore. Yeah. So I created a role, which was, I think this is it, Lambda Dynamo. And what I had to do was, I give myself permission to delete item, get item. I actually don't need delete item, but I gave myself permission to delete, get, put, query, describe, scan, and update. So you create this role, you assign the role to the Lambda function, and then Lambda has access to Dynamo. If you've worked with Bodo, let's actually look at the code. All I had to do was, I created a Bodo session with since this was running from my laptop, I had to use a profile name. Running a Lambda, you don't need a profile name. You need a profile attached to the Lambda function. So actually running in Lambda, you would get rid of this. Actually, it'll give you an error if you don't. And then I create a connection to Dynamo, and then I'm able to do queries against Dynamo. It's really that easy. RDS is a lot trickier because you need like MySQL DB interface or Postgres or PsychoPG for Postgres or something like that. You'd have to package that yourself. I've talked with one of the Amazon reps about making it easier to include those kinds of things, and it's something that they're thinking about. But as of now, you have to include it yourself, and that can be a little. If there's dynamically linked C, it can be really tricky. But there are some good blogs on that.
Can we pause and talk about what Bodo is?
Yes, absolutely. Bodo is a Python library. Bodo is just Python, right? There's no Bodo for other languages. Okay, so Bodo is Bodo is the AWS SDK.
Got it.
That's a great answer. So you create, in this case, I'm creating a resource. You can also create a client. Don't really know the difference. But you could create a resource for Dynamo. You could create a resource for EC2 and spin up instances. You could create a resource for RDS. You could create a resource for Lambda. You can actually create Lambda functions directly from Boto. You can initiate Lambda functions directly from Boto. It's a very simple interface. It's really well designed and easy to work with. But this is the way you integrate or you interact with Amazon resources from Python. That's what Boto is.
When you uploaded your library, the image library, did that go up as a wheel or did that go up as a compile?
No.
Or-
Here, I'll show you. So here is the package. I could have uploaded all of this. I think I only included the Lambda handler, which is my function for creating the tile, the PIL directory, and I think that's actually it. So I created a zip file with those two things, and PIL is actually my copy of the Python imaging library. There's a really nice trick. I don't know how familiar people are with Python. If you've used virtualenv is a Python utility by which you can say, I want to create it. If you don't know it and you use Python, you really want to get to know it. I resisted for a long time. I don't know why. But you basically create a virtual environment, and then if you were to use pip, which is Python's utility for installing, and you install it, it goes into your virtual environment. You don't have to put it in your system. You can have it right there. And that's how I did this, is I created a virtual environment. I pip installed PIL, and boom, it was just there. Kind of. Yes, and if you were to invoke Python, this would be at the top of your Python path. This is where it would look for your libraries first. So really, it's virtual lab. You're creating a virtual environment. You can create a virtual environment, install whatever Python utilities you need, create your Lambda function, and then just zip up that whole thing, and boom, you've got a Lambda package. That's actually in the Amazon Lambda documentation. That's how they recommend how to do it. It works amazingly well, again, as long as you don't have dynamically linked C code. It makes building Lambda functions really, really easy. Since we did talk about it, why don't we take a quick look at API Gateway?
Your 10,000 points, whatever, you're not even doing parallel processing. You're just doing straight as is. You're just shoving it, and it's just trying to do the calculations as quick as it possibly can.
No, I'm actually, so each Lambda function was doing 100,000, and I spun up 100 Lambda functions in parallel. So I wasn't doing each point individually on a Lambda function. Thought about doing that, but that would be that would have been kind of fun. But since I was able to do 100,000 within a couple seconds, I figured that was a good place. And then I just spun up 100 different Lambda instances, and then gathered the data together and summed it up. Those invoke functions that I called, that's what those did. Is they invoked 100 Lambdas, gathered the data, and just summarized.
So then those summarized it, and then you brought them all back together, and okay.
And then did my approximation using all the data that came back. I just added up all the points and then added up all the totals, and used that to figure it out. So I wasn't parallelizing every single calculation, but I was parallelizing in batches of 100,000 points. I think 10,000 points for the pi and 100,000 points for the integration.
So that's what you control, and then in terms of summing, you don't have to worry about how to do that. You just tell it to add. Is that
just
correct?
A couple lines of Python.
Yeah.
So API Gateway is the HTTP front end to Lambda. Lambda itself is event driven. You can trigger it from cron. You can trigger it from an SQS event, something in your queue coming in. You can trigger it from Kinesis. You can trigger. Don't worry if you don't know these things, but you can trigger it from all of these different Amazon utilities. Even RDS now, I believe you can trigger it from. But API Gateway is the HTTP front end to trigger Lambda. It is very, very cool. It is very hard to work with. I'm really looking forward to being easier. You create an API Gateway. You create a part of a URI. So I would go to my API Gateway / Monty Pie, and I could create a get, a post, a put, a delete, all of the HTTP defined actions. And when you do that, you get 4 separate pieces. These glowing dots are tooltips. These are new. It's actually pretty useful. So you create a method request where you can say, this is the data that's going to come in. I have runtime coming. I'm not going to go too deep into here because I'll get it wrong because I'm still kind of figuring this out. You create a mapping here. This is, I don't have one here, but you basically say, I want to map the incoming body, think of it as JSON, map this value to this value, and that's how it gets passed off to Lambda. This is where it gets really complicated. But just know that this utility exists to take get strings or post data or put data or delete data or whatever and map it into Lambda. And then you can do exactly the same thing on the out. The response, let me see if I have one that's a little more interesting.
So it's the details of passing that to Lambda that was the tricky part.
It sounded like how to get that.
It's transforming the data because I wish it just took my post data and my get data and passed it off to Lambda if I don't tell it to do anything else. Flask does that. Django does that. Every single other web endpoint does that. This does not. My guess is eventually it will, but it doesn't. I don't have a good example. But yes, you can map data coming in. You can map data going out. One of the things that's really nice is in Python, you raise an error. You raise an error. That's how you produce an error. You can take the string that you pass to the error, put that into API Gateway and say, if I see this string, raise a 404. If I see this string, raise a 500. If I see this string, raise a 302, redirect. That's how I actually did the Lambda stuff. It's in a different account I'm not logged into right now. It makes it really easy to do these kinds of responses. Again, you have to create these JSON mappings, and there's all this syntax and everything. I would love to do a talk on that someday when I someday understand it. This could be a whole talk, API Gateway alone. But basically, just know that you can map data coming in, you can give it to Lambda, you can map data coming out, and create different response types. And there's always a default one. So if you don't match any of them, usually that's 200. That's your OK response, and you can pass back JSON. You cannot pass back binary data with API Gateway. My original thought was to pass back those tiles as binary data. Can't do it. Not yet. You can only really pass back JSON or something similar to that. I think that's all I got. Any other questions? All right. Thank you.